Just 30 years ago, scientists thought that some places on Earth were sterile. Life there was thought to be simply impossible, just as it seemed to be absent from other planets.
The acid waters, they're very corrosive, yeah.
It has considerable acidity, almost the same pH levels as found in sulfuric acid.
It's got soil and salt and toxic elements like arsenic, cadmium, and nickel.
However, some creatures, known as extremophiles, manage to develop in environments which are extremely hostile for most living creatures. In these environments, microorganisms are the kings. To be able to feed themselves, some animals have strange adaptations. Scientists are studying how they manage to live in water which is as acid as vinegar or as alkaline as washing liquid. In the four corners of the planet, in Europe, America, Oceania, and in Africa, we're going to discover these true hells. This pink lake is Lake Retba in Senegal. Its salt concentration is 10 times greater than that of seawater. Here, with 350 grams of salt per litre, the world record is attained.
Ah, ça y est. Où ça monte?
Okay, it's going up strongly. 310, 320, there 350, it really is a hell. With that kind of salinity, there are no more fish, no more crustaceans, no more plankton. There's nothing anymore, just a bacterial soup. Let's go.
However, in this environment at the limits of life, microorganisms develop massively. They are the only living beings in this salty hell. These microorganisms have a pink pigment. They're so concentrated that they give the lake its pink color. They use this pink pigment to produce energy. It also allows them to resist very high doses of ultraviolet radiation in the same way that the pigmentation of our skin protects us from the sun's rays.
Here, for once, the bacteria are visible to the naked eye, and we can see three sorts of pigments: green, orange, and black.
Depending on the effect of light on the pigment of the bacteria, the color of the lake varies, changing from pink to purple, sometimes without any color at all. The salt density is such that children have fun floating on the water.
Come out now. It's really been too long. It's too salty. Come on. Go on, hurry up. Rinse yourselves.
To resist the sun and parching caused by the salt, the Senegalese collectors rub shea butter into their skin. The men use a stake to break up the salt deposits on the bottom. The women pour out on the ground their basin of 30 kilos of salt. It will whiten in the sun.
My father started work here 15 or 16 years ago.
He worked in the lake. He can't work more than 1 or 2 days a week because it's not good to work anymore.
Okay.
It's not good.
All that of the injury is caused by the salt.
That's all caused by the salt, yes.
And because of that, he can't work anymore.
Despite the fatty protection of shea butter, many salt collectors are the victims of severe skin diseases. The salt from the Pink Lake is harvested to preserve fish caught at sea. It destroys the microorganisms responsible for decay. So how do our extremophile bacteria survive?
In a salty environment, water drains from the cell and the cell flattens like a pancake. To keep their cellular form and therefore to keep themselves alive, the bacteria of the Pink Lake adopt a strategy which is to fight bad with bad. That's to say, they keep up the same concentration of salt on the inside as that on the outside, except that their salt is less toxic than the salt which is found in the Pink Lake.
The bacteria of the Pink Lake have a second secret. They are also adapted to the pressure of the salt thanks to their very original geometric shapes. They are square-shaped, sometimes triangular in shape. This is exceptional because in nature no other species has this kind of shape. Like all living creatures, the bacteria attract parasites, innumerable viruses. Because of that, the lake has one of the strongest concentrations of viruses in the world.
We filter to harvest the microorganisms. We have to quantify them with a microscope. In a simple 1-litre bottle, for example, we can quantify more than 1 billion bacteria. And what's even more impressive is that we found recently that there are 10 times as many viruses.
These viruses have an extraordinary diversity of shapes. Some are round, others are lemon-shaped or like string beans. If there are so many viruses in the Pink Lake, it's because they use bacteria so they can multiply.
The viruses need to use the genetic material of the bacteria to reproduce. In fact, the viruses penetrate the interior of the bacteria by the membrane, and some viruses even have crab-like claws to cling.
With this strong concentration of salt and viruses in the Pink Lake, birds and fishermen aren't likely to be able to catch fish. However, just beside the Pink Lake is found the Saloum River, where salt is extracted too. Despite the lack of oxygen and the high salinity, fish have managed to adapt here.
There aren't any big ones here anyway, not very big ones.
Here, the tilapia's fish are 4 times smaller than they are elsewhere. Here, the salt concentration is 4 times greater than seawater.
This dwarfism is the consequence of the strategies put in place by the tilapia in order to survive in extreme conditions. Salt regulation and reproduction are the priorities because they are vital for the species.
These pockets are the egg sacs of the tilapia. Contrary to the immense majority of fish who release their eggs without a care, the tilapia only produce a few eggs, which are guarded preciously in the mouth of the father. To regulate the salt, the tilapia has cells which act like pumps and which allow them to excrete the excedent. As it goes down towards the sea, the salinity of the Saloum River drops and mud is always everywhere at low tide. However, in this inhospitable environment, a strange fish has adapted to survive.
There, there's one of them. It's coming out of the water. It's really an extraordinary fish that is able to spend most of its time out of the water finding its food, insects, and therefore to avoid fighting for food too much with other species.
Its two chest fins are joined together and act like legs to move forwards or backwards.
Like all fish, the periophthalm has gills. The problem is that the gills aren't efficient for air breathing, so it has developed two types of complementary respiration. The first consists of storing up in its gill chambers, which are highly vascularized, allowing gas exchange that's very efficient. As well, it can breathe through its skin, which is also highly vascular.
So the walking fish will often stay for hours with its mouth open before leaving in search of food in the salty, muddy water. Even if birds rarely land in the Senegal salt marshes, especially at the Pink Lake, there are salty environments which do attract them. Thousands of pink flamingos stop over in the salt marshes of the Camargue. The salinity of the environment is 3 to 8 times greater than seawater. To feed, the little Artemia prawns swallow extremophile algae and are eaten in turn by the pink flamingos. The flamingos filter the water with their beak, which is armed with a kind of comb, and evacuate the salt through their nostrils. The Artemias have a strategy for survival in the saltiest and pinkest of the marshes. The water penetrates the interior of their tissue. The salt, swallowed through their mouths, is then evacuated from their organism. But that isn't all.
The Artemia has superpowers rarely found together in a single organism. In order to reproduce, if there isn't enough oxygen or if the salinity is too high or too low, it lays more resistant eggs covered with a special layer. This layer can resist temperatures between -150 and +100 degrees.
Floating on the surface of the water, the eggs can survive thus for many years before hatching.
The red colour of the Artemia is due to their diet of the red Dunaliella and to microorganisms. This algae produces natural carotenoids to protect itself against salinity and the sun. This is the reason why pink flamingos are pink, because they're at the end of this food chain.
But why do the pink flamingos choose salty lakes as stopovers and as reproduction sites, when they seem to us so inhospitable? Situated in the north of Tanzania, Lake Natron is a saline and alkaline lake. It welcomes half of the world population of pink flamingos. The largest gatherings happen when the lake waters are at their lowest, letting immense crusts of salt appear. However, in this ultra-salty hell, no fish, no Artemia, just the bacteria known as halobacteria manage to survive.
They're the perfect organism for survival if you're happy to live in a salinity of thousands of microsiemens and at a temperature of 50 degrees. But nothing else can live there, not even the tiniest animal can eat those bacteria. It's too extreme.
This lake offers a natural protection for the flamingos against their predators, who can't reach the flamingos because of the broth of salt. The soles of the flamingo's feet is hyper-resistant to the salinity, and the constant temperature of 40 degrees at the surface of the lake doesn't seem to bother them.
It looks very, very uninviting, but this is flamingo dinner. And in fact, it's flamingo dinner, lunch, breakfast, day after day after day. They're very happy eating this because it's highly nutritious. So the high sunlight, the high temperature, the algal productivity can be really, really high. And thus this food can be made day after day after day.
Because of the absence of artemia, the flamingos of Lake Natron have become in fact vegetarians. Here, algae is abundant. Actually, they have at their disposal a large amount of chlorophyll. Chlorophyll pigments allow them to absorb the light, and that energy is then transformed into food.
The chlorophyll is 3, 4, 5 times higher than any other lake. Moreover, because we're close to the equator, it's growing every single day of the year, whereas if you go to the temperate zone, then it only grows in the summer and not in the winter. So the productivity is enormous, and the consistency of that productivity is also enormous. So that's why you can support a high amount of animal life. It's probably the highest amount of productivity of any lake in the world.
Certainly, there's a lot of algae, but their calorific value is low. Because of this, the pink flamingos have to filter 15 times their weight in water each day to get enough food. In the dry season, the area around the lake is a desolate site. In these moon-like, arid, dusty, greyish landscapes, death is often encountered because of water. The death-bringing salinity of the lake has to be left behind to discover more evolved aquatic life. On the other side of the immense salty crust wind several rivers springing from warm water springs that feed the lake. It's alkaline water, which has a pH of 10, whereas drinking water has a pH of 7. But here, the salinity is less, and that's the reason why a curious fish has developed here. Professor Mavuti is looking for Alcalicus, a fish which can stand the salty hell and also the boiling water.
So your mind should be how to get the net down enough to be able to trap that fish. Yeah. Right? Yeah. Right? Go like obliquely. Right? Move the other way. Move. Quick, 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 quick. There. Up. Beautiful. That's nice.
Yeah.
You get the fish in.
Yeah.
Yeah. Just drop them into the bucket. Okay.
If you take here free fish from other river, they will be died immediately because they are not adapted. They are not adapted to survive in this chemical and physical condition. It's so extreme that you have to live here for thousands of years to adapt. They adapted their genetic, let's say, software to improve their metabolism to cope with this kind of environment. You have to be adapted. You have to have a long history behind you that make your DNA good for this kind of environment.
Professor Croza and his assistant are going to test several points to try and establish the survival limits of extremophile fish.
These fish are surviving at the edge of what can be said a safe environment. A little change here in chemistry can make all the life disappearing.
In fact, it's a very fragile ecosystem which can easily be menaced by rapid changes in the external environment. If, for several days, a warm wind blows and temperatures don't drop during the night, then this fragile shelter for life is endangered. Green algae are the basis of the Alcalicus fish's nutrition, so the search for new feeding grounds takes up the greater part of their time. This species was perhaps not quite the same millions of years ago.
They didn't arrive here, they evolved here. And probably that started a time when the environment of Africa was very much wetter, the lakes were bigger. As the climate got drier, they were isolated, and that's the key to evolution. Isolation makes species different.
The rainy season has finally arrived. Lake Natron's colour goes from red to green. The water volume is increasing, and the salts are diluting. In the rivers, the hunting ground of the alkaline fish provisionally gets bigger. The respite will only last a few weeks. Best make the most of it. But the cormorants as well, they're part of this too. The surviving fish now have to reproduce as quickly as possible before the dry season returns. In such an environment, eating and reproducing aren't restful activities.
It's almost 50
degrees centigrade.
Yes.
Wow.
And at this temperature, of course, you don't have any oxygen.
Zero oxygen.
But the alkaline fish have found the answer by capturing the oxygen at the surface of the water. Professors Harper and Crozer are trying to establish their survival limits.
They're responding only to a change in oxygen and temperature. The salinity is staying the same all the way downstream.
The fish take considerable risks to find the best algae. Sometimes it's a losing bet.
They've passed the temperature tolerance limit up to 48 degrees centigrade, but in those conditions, the algal growth is better. So they're darting up, trying to get food and going back, and these two have failed in the gamble. So this species has got a temperature tolerance that is between 48 degrees and about 45 degrees. Now that's that's centigrade, far greater than a human being could tolerate in the bath. Most fish are in the temperature they can tolerate, so the algae is getting grazed. Those that are capable of withstanding a higher temperature, darting in, eating, darting back, will get better food. So they're the ones that are taking the risk, and the reward is the food, the risk is getting cooked.
I'm sure that the DNA analysis will solve some scientific problem. Who knows? Maybe from knowing how the life can survive, this at the end can be of help for us, because we have to survive as well.
In spite of its inhospitable nature, Lake Natron is an important stopover for many migratory birds. Let's leave the Atlantic for the Pacific. In California, another ultra-saline lake, scarcely more welcoming, is however another well-loved bird stopover. Thousands of migratory birds come here to double or triple their weight before taking on their long voyage towards South America. However, we're not below the equator, and extremophile algae are therefore clearly less prolific. So how do we explain such a strong attraction?
Many of the bird species here have found the alkali fly to be a rich source of protein. The local Native Americans also found the alkali fly to be a rich source of protein and would harvest the fly from the nearshore regions. And they were known as the Kutsadika, the fly-eating people.
The shores of Mono Lake house the largest concentration of alkali diptera in the world. To evolve in the salty hell, alkali diptera grew itself its own diving suit. These slender flies have long hairs. They have them everywhere, even on their heads. These hairs trap the air around them, thus creating a protective air bubble. This ingenious system allows them to reach the carpet of bacteria upon which they feed.
If you drink this water, you'll see it has a bitter, soapy taste due to the sodium bicarbonate and sodium carbonate in the water.
Over centuries, the accumulation of carbonates and calcium has formed enormous tapirs. And it's from these carbonates that the extremophile bacteria have massively developed.
And just that little bit I drank, probably about 1 million bacteria I ingested in that couple drops of water.
Thanks to this overabundance of bacteria, and therefore of food, Mono Lake holds another record, that of the number of artemias.
Its population in the middle of the summer can range between 3 and 12 million shrimp in the whole lake. This summer population produces resting eggs that fall to the bottom of the lake and rest over the winter. So the next spring, when the waters warm up, these eggs hatch out and the cycle starts over. Sometimes in the summer, you can see just how abundant the artemia are when the current conditions cause one water mass to go underneath another, and the artemia will collect in these long windrows.
From this, seagulls and other migratory birds can choose between flies and the artemias.
The grebes, though, eat almost only the shrimp. And they capture these shrimp when they swim through the water, and they have special glands that deal with that salt load that they get from eating the shrimp out of this salty water. The gulls, on the other hand, get a lot of salt load in that food, but they then go to the freshwater streams that come in at the west end of a lake and drink a lot of water to help deal with that salt load.
A few wing strokes from Mono Lake, there was once another bird paradise. Here is what is left nowadays of Owens Lake. A century ago, the water from this lake allowed the inhabitants of Los Angeles to water their lawns.
Owens Lake, before the water was diverted from Owens Lake, it looked very much like Mono Lake. It was a salt lake like Mono Lake. There were millions of birds here. It was a very productive place. But then when the water was taken away, Owens Lake has become one of the most alkaline places on Earth. If there was ever an alkaline hell, this could be it.
Even the alkaline flies have fled. The salinity of Owens Lake has become 4 times greater than that of Mono Lake, and the ground temperature can get above 66 degrees. Only bacteria survive in salt crystals.
The red color in the water is caused by 2 very salt-tolerant bacteria, Halobacter and Helicocci. They're very small. They live in the hot waters here, the hot temperatures and the very salty conditions. They're so small that about 500,000 will fit on the head of this pin here.
This lake has turned into a toxic desert disturbed by tornadoes. Its dust burns skin and eyes and gets in everywhere.
Over 200 locations across the lake bed where we have monitoring stations that measure what's happening out here. We measure wind direction, wind speed, temperature, and really most importantly, the sand motion. If you've seen footage of the Twin Towers when they collapsed on 9/11, the amount of dust that came off of those, the levels that we have here on Owens Lake are comparable to the amount of dust that was generated during when the Twin Towers fell.
Pushed by the wind, dust clouds can menace places sited within a radius of 100 kilometers.
So these are very, very fine soil particles, and they lodge very deeply into your lungs, and that can cause health problems. In addition, there are toxic materials out here, arsenic, cadmium, and nickel, which can also cause health effects.
Is Owens a unique case? Do other places exist that have been really turned into hell through man's actions? Take a look at this Spanish river. As the name says, Rio Tinto has a reddish glint. Is that really its natural color?
Rio Tinto is unique. It's 100 kilometers of river with its pH around 2. That means as acid as lemon juice or as acid as sulfuric acid. It's practically the most sulfurous river in the world.
It's also one of the most polluted. Rio Tinto carries 2 tons of zinc, 1 ton of copper, 100 kilograms of arsenic and 10 kilograms of cadmium every day to the ocean.
Here we can see this intense red color, which is due to the heavy concentration of iron.
In fact, the source of the river is in Andalusia, where is found one of the biggest open-cast copper mines in Europe. For a long time, it was thought that the determined exploitation by mankind for over 3,000 years was the reason for its acidity. But scientists have shown that this acidity is of natural origins.
Before coming to the conclusion that the acidity of the river was natural, some of the region's heads thought the opposite. They wanted to fix it. But whatever they did, by adding chemical products, nothing seemed to work. The pH stayed highly acidic. If we take a sample of water and we pour this reactive substance with a neutral pH, the solution immediately turns red because of the acidity in the river.
If mining activity isn't in question, then what is responsible for such acidity? In order to know this, it's necessary to go back to the source of the river, there where the pH is 1.7. This means very high acidity.
The most important actors in the acidity of the river are 2 bacteria, Aciditas bacillus and Loctus spiritus. They produce sulfur, which has a high pH, and which gives the river its high acidity. The red color comes from the dissolved ferrous sulfate in the water.
Because of its high acidity, the river is dangerous for most living things. An old story recounts how a certain Diego Delgado once threw a living frog into the river. That frog died before it could even get back to the bank. The acidity of the river is so high that even big mammals still use it to destroy their parasites. Trying to cross it could prove fatal for this less than prudent ant. However, in this chemical hell, life manages to trace its path. Thanks to the energy brought, amongst others, by the sun, which they transform in energy, microalgae grow.
They're taking their energy from the light of the sun. A very intense green color which comes from the action of solar energy on chlorophyll. The little bubble that we can see there are the oxygen produced by the algae.
If the algae manage to produce oxygen by staying at the surface of the water, what do they do to combat its acidity? Because of these walls which partition the algae cells, acidity doesn't get higher in their center than a pH of 5 to 6, even if the river water has in places a pH of 1, that is to say the same acidity as a human stomach. In order to survive, all these tiny organisms keep their pH close to neutral by evacuating to the exterior all those dangerous chemical elements. These diatoms have a shell, a real bone structure which protects their motor, these little green elements full of chlorophyll. Like the algae, diatoms transform solar energy into fuel.
The number of species found in the river is of the order of 1,300, including all the types of fungi.
The further one goes down the river, the more the algae and the fungi are found. But the sulfuric oxide deposits bear witness to the toxicity of the environment. A unique ecosystem has little by little established itself after the bacteria. At its peak, here's Heliozoa, a sort of amoeba. This predator moves around by long, sticky filaments, which give it a sun-like appearance. Its rays are deadly. This eugleniid is, unfortunately, about to learn that to its cost. The euglenids are very common in extremely acidic environments. They feed on bacteria. These two red pigments, which look like eyes, serve them to detect the sun. They also stimulate their flagellum in order to direct themselves to better light conditions. At the surface limit, the algae, which are more and more numerous, are populated by the halobates, also known as water spiders or walkers. They seem to slide over the water's surface. Their feet are covered with hairs covered with an oily secretion upon which water slides. It is by using this rostrum that it catches microorganisms or dead insects that have been trapped by the acidity. Through all these species, Rio Tinto is nowadays a protected acidic biotope. You have to go to New Zealand to find the most extreme acidic environments.
Frying Pan Lake is the hottest, most acidic, large body of water in the world. The average temperature in this lake is 55 degrees centigrade, but there are many hot spots and many acidic vents.
Dr. Hugh Morgan is an acidophilic bacteria hunter. He often goes to Waimangu to study the ecosystems.
Temperature is 69 degrees.
69?
Yeah, it's quite high.
Good for thermos.
Here, only bacterial life is possible.
It's 2.5 to 3 pH.
When the temperature drops below 67 degrees, the algae can grow, and then an ecosystem becomes possible.
The temperature on the surface of this algal film is 45 degrees. It is teeming with life, lots of flies and larvae.
These larvae merge together in a ball, seeming to pass successively upside down and vice versa, in order to expose themselves as little as possible to the deadly acidity. They are also the result of strange adaptations. They have a gland that acts like a kidney by filtering acidic elements. These superlarvae also have 2 telescopic respiratory tubes, according to their need of air. But the most spectacular of their adaptations are their little feet with claws that are usually never found on fly larvae. They allow them to hang on to algae so that the currents won't pull them into zones with a deadly pH.
We need to make sure this is really tight. Don't want it to come off. And we'll just adjust the lens. Okay.
Some acid lakes also are connected to each other by rivers. There the temperature is less, but this poses a big risk for the larvae which can't hang on.
Doesn't look as bright as it did.
Oh, it looks like it's being corroded.
Yes, the acid waters, they're very corrosive. Yeah.
Really low pH.
It doesn't take long.
The surviving larvae have also to face the beak of the fantail, a bird that is a specialist in hunting them on the surface. Despite all their efforts, many larvae don't become mature because of the rapid changes in pH due to the acid sources feeding the lakes. Larvae that manage to transform into flies have to be imaginative to find those calories. Some of them use the mixture of larvae so as to recover the precious bacteria. Others take advantage of the humidity of rare plants and fungi which grow here to feed off that.
This plant is at the extreme edge of its range. Its roots are at 46 degrees and it's very acid pH. Nothing else can grow here.
Like fly larvae, plant roots establish themselves at the surface so they can oxygenate. They have also developed proteins which allow them to resist the heavy metals which are very much part of the acidic environment.
Acid pools are the result of bacteria that use sulfur as their food source, and they produce sulfuric acid, which lowers the pH. And this produces these devilish, poisonous conditions, which only they can live in. We couldn't live in that environment.
Most of these craters aren't even 900 years old. They owe their unusually acidic nature and their color to the work of extremophile bacteria who degrade heavy metals.
In this case, the green-yellow color is due to sulfur, colloidal sulfur, which is suspended in the body of water. And then we get orange colors due to arsenic and antimony, purple colors due to manganese, white due to silica on the surface, and red due to iron deposition, and black due to iron sulfides.
The stiltfoot, this bird with leather-covered feet, doesn't seem to care about the environment. But what can it find that's living?
pH is about 2.5, which is about, this is like vinegar.
However, many larvae grow in this vinegar. They breathe through this tube which comes out of the water. Sheltered from the main predators, this spot is a real reproduction site.
There is a very dense ephedrid fly population here. They breed and the larvae grow and develop in the pond, and we think these are the main food source for the leeches that are present. We have a very unusual form of life in these pools. It's a leech. It grows at pH 2 and 35 degrees, and it's very unusual.
The inventory of extremophiles and their ecosystems has only begun. Their discovery has immediately led to the formulation of new hypotheses of the origins of life on Earth and perhaps elsewhere.
We know that the primitive oceans were highly saline environments, that extremophile microorganisms weren't the result of adaptation but are living fossils.
Scientists believe that acidophilic hot pools on other planets may have been the source of the true origin of life.
This river is so extreme that we can use it to understand what life is, and whether these forms of life could reproduce themselves on other planets.